Consider the function f of x equals 3 sine x plus 3 cosine x on the interval from 0 to 2 pi. On the graph to your right, I always create a little bit of cushion left of the left endpoint and right of the right endpoint. We only have to investigate the part of the graph that's between 0 and 2 pi. Those are highlighted in red and blue. Excuse me. Our first derivative, we're going to have 3 cosine x minus 3 sine x. And then the derivative of our first derivative will be negative 3 sine x minus 3 cosine x. Let's investigate the second derivative. The second derivative is equal to 0. We're checking for a possible inflection point. Factor out negative 3 from both terms. Negative 3 factored out will leave sine x plus cosine x behind. Negative 3, if you divide that out on both sides, you're left with sine x plus cosine x equals 0. I chose to move cosine x over. It goes negative. Now we're looking for angles where sine of the angle is equal to negative cosine of the angle. If you remember from your unit circle, sine is the y-coordinate at any angle, cosine is the x-coordinate at any angle. So basically, we're looking for angles where the x and the y value only differ by a sign. The two angles that you guys gave me in class were 3 pi over 4 and 7 pi over 4, and those are both correct. At 3 pi over 4, cosine is negative square root of 2 over 2. Sine is positive square root of 2 over 2. At this other angle, cosine is positive square root of 2 over 2, and sine is negative square root of 2 over 2. They only differ by a sign. So what we do is, remember, we're also investigating only from 0 to 2 pi. So both of these angles are potential inflection point values. Let's scroll down. In the second derivative, we're going to test numbers between and around 3 pi over 4 and 7 pi over 4. We also have to be mindful not to go all the way to 0 or all the way to 2 pi because we're looking for open intervals. So somewhere between 0 and 3 pi over 4, you guys suggested pi over 2, that's a great choice. If you test the second derivative with pi over 2, you get negative 3 sine pi over 2 minus 3 cosine pi over 2, and that goes back up here to the second derivative. This comes out to negative. Now, if you're looking for an exact value, it's negative 3. Between the critical numbers, that would be between 3 pi over 4 and 7 pi over 4. You guys recommended pi. That was a good selection. If we test pi in the second derivative, f double prime of pi, that's negative 3 sine pi minus 3 cosine pi. If you substitute pi in for your angle, calculate all this stuff out, you get a positive 3. We just need to know that it's positive. And then finally, there was a small window between the second critical number and the x-axis. And so we needed to pick an angle between 7 pi over 4 and not 2 pi because that's the end of our interval. And you guys recommended 11 pi over 6. Excellent choice. F double prime of 11 pi over 6. When that angle is subbed in, you get a negative 3. All we need to know is that it's negative. So back to our number line. From 0 to 3 pi over 4, we know we're concave down. We're also concave down between 7 pi over 4 and 2 pi. And so I had to unite those two intervals. I just used a union symbol. We were concave up between 3 pi over 4 and 7 pi over 4. And so concave up was this interval between 3 pi over 4 and 7 pi over 4. So we have two intervals of concave down, one interval of concave up. That means we have two inflection points because the concavity changes here and the concavity changes here. Subbing those two angles into the original problem, I'm going to scroll back up. I made a little note there. Visually, you can tell that the concavity changes here. When we sub 3 pi over 4 into the original function, and remember for inflection points, you use the original. F of 3 pi over 4, sub that angle in for x, use your unit circle values, you get 0. So this inflection point is 3 pi over 4 and 0. The other place, 7 pi over 4, when subbed into the original function, also leads to 0. So these orange ordered pairs are they're both inflection points. Concave down 0 to 3 pi over 4, also from 7 pi over 4 to 2 pi. That also matches our number line part on number 4 below. And then we were concave up between 3 pi over 4 and 7 pi over 4. And so we pretty well investigated that problem pretty hard. Now, remember, concavity, inflection points, they're all based on the second derivative. Increasing, decreasing, and critical numbers where the first derivative is 0 or undefined, that's all based on first derivative. Let's look at one more, and on this one we're going to sort of bunch them up, first derivative and second derivative. Consider the function f of x equals 3x natural log x. Let's take our first derivative. Our first derivative, we're going to have to use product rule. So we have derivative of the first, that's 3, times the second, that stays natural log of x, plus the first times the derivative of the second, and that's 1 over x. The x's cancel. So our first derivative is 3 ln of x, natural log of x, plus 3. Our second derivative is the derivative of the first derivative. So we have 3 times 1 over x. This 3 goes to 0. So our second derivative is pretty simple. It's 3 over x. Let's go back to the original function. Natural log is only defined for positives. It doesn't even like 0. If you type in natural log of 0 or natural log of a negative, you're going to get an error. So this graph gets close to the y-axis, but it doesn't actually touch it. And it's pretty much just like a little check mark. We do have a low point, so that's a relative minimum. We'll investigate that towards the bottom. But this graph is always concave up. You notice that? It's never curved downward. It's always curved up. That second derivative for any x value in the domain of the function, which is anything positive, 3 divided by a positive number is always positive. So that's why this graph is always concave up. Let me scroll. Critical numbers, you have to really pay attention to whether there's an f prime or an f double prime. This one's a single derivative, so if we go to the first derivative, we're going to locate that low point on the graph, the one that was shaped like a check mark. We're going to find the bottom of it. So we're going to take the first derivative and set it equal to 0. Subtract 3, divide by 3, and we get natural log of x equals negative 1. To solve for x, we have to exponentiate with e. E and natural log are inverses, so they'll cancel one another. When we exponentiate both sides with e, we get x equals e to the negative 1. You can also write that as 1 over e. So our critical number is when x equals 1 over e. Let's go a little farther. To verify that that is the minimum, you can use what's called a second derivative test. What's that all about? If you take your second derivative and you plug in the critical number from the first derivative, remember our second derivative was just 3 over x. So our second derivative with 1 over e plugged in is going to be 3 divided by 1 over e. That comes out to 3e. Because the second derivative is positive at our critical number, we know that the graph opens upward and that this x value is a low point. Since f double prime of 1 over e is positive, the graph is concave up at our critical number, and that forces us to have a relative minimum. Now, the point on the graph, the original, you have to put 1 over e into the original. 3 times 1 over e times the natural log of 1 over e. Natural log of 1 over e is -1. That's where this negative comes from. 3 times 1 over e, that's just 3 over e. Remember that the number you plug in and the number you get as an answer, that's an ordered pair. This ordered pair is where the relative minimum is in our graph. I'm going to scroll back up. Okay, so let's remember our first derivative was equal to 0 at 1 over e. Because the second derivative here was positive, that forced it to be concave up, and that means it's a low point. Our graph is always concave up throughout its domain, so concave up from 0 to infinity. The first derivative is 0 at 1 over e, and then our original function at 1 over e was -3 over e. This ordered pair is that low point.